Hi everyone. Welcome to this session on software memory tiering. We are a couple of folks from VMware. So my name is Arvind Jagannath and I'm a Senior Product Line Manager at VMware. So I basically deal with a lot of the infrastructure enablement and I'm basically a platform product manager at VMware. With me I have Sudhir Balasubramanian.
So good morning. My name is Sudhir and I'm a Senior Staff Solution Architect. So I'll be focusing more from an application perspective. So essentially, Arvind will be talking about infrastructure and how VMware Software Memory Tiering works. And I'll come top down and I'll talk about some real world use cases using Oracle workloads. Take it away.
Thanks. So I'll start by presenting some of the core value proposition and what VMware vision is after I present the value prop. So essentially, VMware, if you can see, as you will see after the presentation, by the time this presentation ends, we have sort of a head start in terms of being able to adopt the CXL technology. So let me actually first cover some of the competencies. So VMware, as you all probably know, it has been a hypervisor operating system. So the beauty of virtualization is that it lends really well to all the underlying hardware changes, the hardware innovations that are happening in the industry. So one of such innovations is the CXL technology. So what we are doing is, with any new hardware that comes in, VMware virtualization makes it very easy to adopt that new technology. So what that means is, you can bring your older operating systems and applications from maybe 3 years ago, and you can still run it on a virtualization platform without any changes at all. So the operating system will make sure that everything is abstracted away. You get a clean, easy interface that you are used to as usual to run your application workloads and run the same old operating systems. So the other core competency is with respect to resiliency. So VMware was built with a premise that we want to offer customers the resiliency that they need to maintain the performance of their workloads. So we actually came up with something called Distributed Resource Scheduler, which is DRS. So what DRS gives is, it gives a very risk-free environment to customers. Basically with DRS, what we do is when we can bunch together a list of hosts together and create a resource pool of compute. And what happens with that is that if a specific workload cannot sustain a performance level that it needs with a specific host, DRS can take the action, it keeps monitoring for that workload, and it can automatically takes the action to remediate and make sure the workload finds an appropriate host where it can run that workload. So in that sense, DRS is really important, and I don't think any other clustering system or operating system is capable enough to give such a feature or capability today. The third thing I want to mention is on the ecosystem. So VMware is one of the only commercial sort of hypervisor that is available in the market today, which means that we have to work with very closely with a long list of ecosystem partners. So we have partners across the board. If you look at our VMware compatibility guide, we have partners across storage vendors, storage array vendors. We have HBA and networking vendors, basically on the IO front. We have CPU vendors we work closely with, and of course, OEM partners are important. We work very closely with our OEM partners. Some of our requirements are driven by OEMs also. So if you look at the compatibility guide or the HCL for VMware, you will see like tens of thousands of partners that we have, and devices that we support, and arrays that we support, CPU, different versions of CPUs, etc. So this is a very good advantage of VMware, where we already established a base partnership and we have a way to self-certify. We make sure that customers or partners can easily come in. Any new partner can come in and actually certify their solution with us. Next, at the bottom of this slide, you can see some of the innovations that we recently did over the last few years. So VMware has been front and center in providing sort of getting all these newer technologies that are coming up in the industry, following the industry trend and immediately adopting those. And we make it such that they are easily available for the VMs also, for the guest operating systems that run on the hypervisor. For example, we came up with the pass-through devices. So we introduced the pass-through device capability, and with the latest version of vSphere 8.0, we even have an ability to vMotion or apply DRS algorithms to some of those pass-through devices. So this is like a very new innovation that I don't think anybody else in the industry has it. The next thing is, things like GPUs and sharing and assignable hardware. So a couple of years ago, we introduced something for example, called BitFusion, which is, an ability to host a single server that can have all the GPUs and have, all the other hosts in the cluster that don't have the GPUs, but that can still virtualize those GPUs and can run GPU-based workloads. So basically what that means is that VMware is such an integrated cluster, integrated environment that you could actually supply or support such a use case where you don't necessarily need such a hardware infrastructure on every single host where the workload exactly runs, which means that you have the ability to share and assign hardware on demand. So that's a unique advantage of VMware also. The third thing is, which we recently introduced, is on the SmartNIC side of things. So these are just some of the innovations I'm mentioning, but there are a lot of others. So with SmartNIC, we have the ability to now run the embedded version of ESX within the device itself, which means that we have a capability of monitoring and making sure we can use the single pane of glass, and we can control and manage, separate networks, especially useful for a service provider like environment. Plus, we can provide all the offload capabilities, the speeds and feeds necessary by offloading it to a SmartNIC or a DPU, as it's called. Similarly, with accelerators, we have introduced some accelerators specific to a lot of use cases like the telco use case, and we are able to bring that innovation easily. We even have support for things like custom FPGAs for specific use cases that customers are able to use today and widely deploy. So next, I want to just quickly walk you through one of the trends that we are seeing. So I won't cover this a lot because most of you are probably aware of this and have seen this number of times. So there is a digital transformation of businesses that is happening over the last 3 to 5 years, or even more, I would say. So data is growing really rapidly. We have seen that by 2025, for example, IDC predicts that almost 176 zettabytes. I don't even know if it's a million or a billion petabytes. So zettabytes is a huge quantity, I can say that. And that kind of data is getting generated, which means that data is being generated at a faster rate than ever before. Over the last 2 years, probably we generated more data than the previous 15 years or 20 years. So this is coming up because of a lot of different trends with IoT and social media and a lot of different ways of using devices and storage costs getting lower. A lot of data is automatically being generated also because of replication and data protection, and then faster CPUs. So a lot of trends are driving the growth of data. Along with this is a challenge which comes for businesses, which is how do they actually make use of this data to get valuable insights? So they need to run some applications like AI, ML, or big data analytics to process this big amounts of data. So they need a large amount of memory for that. They need to scale up their systems. Scale out solutions may not necessarily work because that takes a lot of lift and shift. And so a lot of customers will look for a scale up kind of solution. And these are especially useful when we talk about memory technologies and we'll see how we can scale up, for example, memory to ensure that such applications will be able to run. The other important thing here, the important point I wanted to mention is about the real-time nature of applications. So a lot of these applications need to be real-time, like in-memory databases, because customers do require that insights are gathered quick, fast, and then they have a need to process it at the same moment when data is generated. So there is a IDC prediction also that 30% of global data will be real time by 2025. So if you look at the left side is where we see some of the trends. So we see that in terms of the growth of data, we are seeing a data explosion. There is a need for customers to gather that insight they need from all this data, and that is a key point here, which means that data has to be processed in real time, and they have a desire to extract more out of the data. And the problem is that the software has been upgraded, it has been modified. We have a lot of applications that can make use of this data, but then hardware is not catching up to actually support that kind of software. So, for example, we have all these AI ML applications being written. We also have the underlying infrastructure environment, the software that's required to run these applications, but the hardware is just not catching up. And that's where technologies like big memory and CXL and software memory tiering come into picture. So on the right, you see some of the pain points that customers are undergoing today. So then they have a need to scale the infrastructure to address this data growth. They also need in-memory computing. So DRAM is expensive. So if you look at a typical configurator from, for example, Dell's or HP's, you will see that DRAM almost occupies like 50–60% of a good server cost, which is just phenomenal. So we are trying to solve the TCO issue that customer has today. There is also a need for monitoring and remediation. Like I mentioned in the previous few slides, monitoring and remediation is something that ESX and VMware does really well, which means that we can actually put more into our operating system, into the hypervisor, because hypervisor is placed so well that it can monitor every single workload, and it can monitor the compute resources, the memory resources, and the storage resources, and it can ensure that all those are provided for when the application needs it. And so for those things, VMware already has monitoring in place, and I'll talk about a new feature that we introduce in the upcoming slides. So really the point here is that VMware's big memory vision, which is the need to actually address some of the pain points that customers are running that I presented so far, starts with software tiering, which means that we have a system where we actually incorporated a lot of the logic and the algorithms required to actually perform this tiering and perform it in an agnostic way, in a very transparent way, so that applications and operating systems do not have to be modified. So in terms of the software tiering on ESX, I'm trying to go through some of the advantages that are present when we actually have such a tiered system built within the hypervisor itself. So one is, why are we even doing this? The reason is simple. It's to provide higher density and more capacity. I mentioned lower TCO. I mean, DRAM is obviously expensive. With DDR5, you will start seeing a sort of a bump in the prices again, for at least for some period of time. So definitely software tiering can help address that when you actually combine DRAM with other tiers of technologies, memory technologies. So the other important thing is on the density part of things. So as you can see, we have limited slots and limited capacity on a typical host. So when customers talk about scaling up rapidly or providing more capacity, it's an issue when customers have to provide a 64 gig DRAM into specific slots. They really are not able to scale to the amount that their cores need, or the kind of cores that are even coming up in the future, in the next couple of years, they are going to be up pretty significantly. So to support that, we do need the memory technologies to evolve and to see if there are ways where we can provide more capacity on a single host. So other thing which we provide is we ensure minimum performance degradation, which means that we add all the predictability, the hot and cold page placements. I mean, the page placement is basically when you think about memory being divided into chunks and being replaced continuously, being monitored for hotness or coldness, for activity, and the hypervisor is in the best position to actually ensure that a particular VM has its performance needs satisfied. So which means that we can ensure minimum performance degradation by actively monitoring and making sure that the page placements happen consistently. So the other thing is transparency, which means that even though you add these different tiers of technologies, memory technologies underneath, what ESX presents to all the VMs to consume is a single memory address space, which means that, like I mentioned before, there are no guest or application changes required. You can continue running any operating system. You can continue running the same applications as before. So all that the system admin, the VI admin sees is that he gets more memory now. And this memory is handled transparently. Yeah. Yeah, we don't have tunable. Yeah, that's a question which comes up very often. We don't provide any sort of tunable because we don't want customers to be have to deal. First of all, it's a management issue, which is because customers have to be aware of how their workloads are running, and they have to go and specify certain settings for each sort of workload, or even at a VM level, VM granularity level. And then we also want to make sure that we actually have control over the entire memory space, which means that we can ensure that for example, if there is a specific workload that has a specific need, then we can provide that immediately based on the performance requirement. So we continuously monitor, and over a period of time, you will see that the application will get the performance it needs without having to do. Yeah, so it will be nice to have. What we do have is, on the compute front, we do have some QoS policies. For example, even on our DRS, we have some QoS policies that you can apply, but not directly on the memory front, because memory, we feel that memory is such an underlying piece of technology that we don't need such specific controls. Having that control at a compute level or at a DRS, at an overall holistic compute resource level provides more sort of, flexibility or more ability to run workloads better for customers. So the next thing is, I mentioned DRS. So all that we do in terms of hardware, newer hardware, we have a policy where we actually say that, any new hardware technology that comes, and right now we came up with the software tiering technology that's automatically fed into DRS, which means that, we have continuous monitoring of how memory is looking for each of the VMs, how it's looking across the host, and even across the cluster. And DRS is this single entity across the cluster that can manage how this memory is being used. And it can ensure that, if there is a specific performance need, then the mitigation is done immediately. The other thing is on fairness. So a lot of the tiering solutions out there, they don't really have a way to ensure for fairness. For example, if you have a hypervisor operating system and you have a particular rogue VM that is running on the hypervisor, you could have a case where that rogue VM could occupy the entire DRAM, and it could actually make things difficult for the sysadmin. So what we ensure is we continuously monitor for such rogue VMs which are trying to hog the memory, or they're trying to unnecessarily take up memory. We ensure that the other workloads which have been waiting for a long time get get some amount of memory so that they can run as well. Which means that we can have that guarantees across the different VMs, across workloads. The other thing is zero configuration changes. So there are no special tiering settings, no QoS, like you said, QoS settings that are required either at the VM level or at the host level that needs to be configured. We want to make it plain and simple for our customers. The last point which I said I'll come to is the VMMR, which is vSphere memory monitoring and remediation. So we worked with the CPU vendors. We wanted to ensure that all the newer CPUs that are coming in the industry, we actually take CPU specific statistics. The CPU has a way to monitor, or the architecture, the hardware architecture has a way to monitor the memory bandwidths, and we actually surface those memory bandwidths now into the vCenter. And we can do this for both the VM and the host level, which means that customers now have a clear insight into how their workloads are looking in terms of occupying or consuming these different memory tiers. So for example, we added this capability for Optane persistent memory and for DRAM. So what that means is, customers can continuously monitoring how their bandwidth is looking, their miss rates, etc., are looking across these different tiers. And they can then size and change based on their application profiles. Yeah, I mean, this happens at at the level of sizing the VMs. For example, if you want to size VMs and you want to ensure that there is, or you want to size the host differently, right? We actually have these ratios of different tiers pre-decided at the host configuration or at the sizing time, right? So we don't necessarily need any further configuration after that. So you could have a cluster, for example, where you could have a DRAM only host. You could have a ratio of 2:1 or 4:1, and then you could have this different varied set of hosts, and then DRS takes care of which host is most appropriate. You could, for example, start with the 4:1 configuration, which gives the lowest cost, and DRS will decide where to place the workload based on the demands of that workload. So yeah, this is what we actually did in terms of software tiering over the last last couple of years. So we made changes into our memory management layer, the DRS and the scheduler. And we actually took, in this case, the lower cost memory happened to be Intel Optane, but, we could actually potentially use any sort of technology underneath. So what is the relevance for the future? So in terms of the CXL, we are already talking to a bunch of memory vendors across the board. So we are talking with some of the typical SSD vendors, the top 3 or 4 memory vendors. And we are actually trying to partner with them, and we are trying to see how we can use some of their technologies. A lot of these have use cases of for lowering the TCO, because TCO is a big problem for customers. There is also the memory expansion use case, memory capacity use case, where customers want to increase their capacity, or bandwidth use case, because bandwidths are limited for a lot of the workloads. So sometimes customers need that bandwidth, and we are working with some of these vendors. So all these vendors provide different, a varied range of technologies, and we have the ability now, since we have the software tiering built into the ESX kernel, we have the ability to now use any of these technologies, and it's just a matter of making sure that we actually are aware of the latencies and the performance requirements for each of these, and adjusting our tiering according to that. So these are some of the ways in which we could perform our tiering. So we could use lower cost, slower memory. We also recently demoed a use case where there is a CXL device. This was at recently done Explore, where we have a session. It's available online, where we demoed that you could actually have a CXL interface to actually another device which provides more memory. It's attached using PCI, but acts like a NUMA, and you could have NUMA-like latencies to access that CXL attached memory. So you could have a variety of ways in which we could add more memory, and we could, in addition, use the software tiering approach that we already built in. And we are also planning on productizing software, the CXL 2.0. We are already working on enabling CXL in our base operating system. And then at some point, CXL 2.0 comes with all these nice things about error recovery and control, and it provides for all the capabilities for ensuring cache coherency and cache consistency. So making sure that we can use these CXL devices like memory. So we are definitely looking to productize it, and I think by next year we should have a clear view of which specific vendors we will be working with, and we are already starting on some of that journey and partnering with some of those vendors. So this is just a quick view on how the logical view versus the physical view looks. So on the physical side, you see a lot of different tiers. And finally, how all these fits together. So basically, you start with sizing it on the host level, which is the square box in the middle. And then once you size it, the VMs will automatically, dynamically adjust their size, tier sizes. And they will have the capability the host will ensure that the VM gets the tiers it needs based on the active memory usage, for example, of the workloads. And then you will have the VM monitor and the corresponding the page placement algorithms in place, so that the pages can move between the different tiers. And there is continuous monitoring on the bandwidth and miss rates and the performance for each of those different tiers, and basically to monitor how the VM is performing. And finally, on the left is the DRS. DRS ensures across the cluster that the VMs are receiving a consistent performance, and they can make sure that if a VM is not getting that performance, they can move it automatically. And this is also tiering aware, and it's aware of how each host is using the different tiers. So now I'll hand it over to Sudhir from VMware.
So I guess you guys can hear me. So this is good. All right, let me move on to the next slide here. So essentially, I'm going to be talking about something completely different, right? So I won't be talking about software memory tiering. I won't be talking about CXL. I won't be talking about tier 2 memory. I'll be coming from an application perspective, right? Because what good is an infrastructure? What good is a platform? What good is any technology or any tools if applications really can't make use of it, right? It has to make sense. At some point of time, the SAPs of the world, the Oracles of the world, the SQL servers of the world, or big data, whatever you have running in the shop, should be able to make use of the technology in order to use it effectively, right? So I'm going to be using Oracle workloads, Oracle databases as a use case here, right? This doesn't pertain only to the Oracle workloads per se. You could apply that to any workloads that is running in your shop, right? So quickly to summarize what Arvind spoke about, right? Essentially, with VMware vSphere as a platform, essentially what we do is we throw a blanket, right? What we do is we just throw a blanket across all these disparate memory components, be that DRAM, be that tier 2 memory or NVMe and so on and so forth, right? We kind of obfuscate the entire layer. We lay the burden of moving the hot blocks and the cold blocks on the hypervisor so that the application owners or the DBAs or the software owners, they don't have to worry about the hot block or the cold block. All they have to worry about is what I need is a chunk of memory, and I know ESXi will do my job for me, right? So again, when I talk about business critical workloads or business critical application, I might refer to Oracle, but that could be the SAPs, the Oracles, or the SQL servers in your house. I want to move over to the next slide here, right? And I'm going to show a real world use case. So essentially, we took two servers. These two servers were completely identical in their design. So each server had 4 socket, 24 cores per socket. So 4 socket, which means 4 NUMA nodes. Every server had 1.5 terabyte of DRAM, right? And 3 terabyte of tier 2 memory. So the server on the left-hand side of this illustration, that's a software memory tiering server. So that's why you would combine your DRAM and your 3 terabyte tier 2 memory, right? And you get a total of 4.5. The server on the right-hand side, that's DRAM mode only, which means the software tier 2 memory, that's not taken into the picture here. Again, servers are exactly the same. This was ESX 8.0, the latest and the greatest. And the servers are exactly the same, right? From a patch level perspective, from a security perspective, so on and so forth. So server on the left, software memory tiering server. Server on the right is the DRAM mode server. Okay, and if I have to if we have to do a bit of a deep dive into the whole NUMA architecture perspective, right? As we said, every server had 4 sockets. So server on the left-hand side has 4 sockets, 4 NUMA nodes, and you can see the distribution of the DRAM and the tier 2 memory. So every NUMA node had 384 gigs of memory and 768 gigs of tier 2 memory. And this is of utmost importance. And the reason why I wanted to show this picture was when we come to the virtual machine design, when we start stacking up virtual machines, you would see that we are able to stack a lot more VMs when we use software memory tiering and run a lot more workload than you can on a DRAM-only server. So keep that in mind. Every NUMA node had 384 gigs of DRAM, 768 gigs of the tier 2 memory. Right-hand side, it had only 384 gigs of DRAM per NUMA node. Okay, so that was from an ESXi perspective, right? So if we were to move a level up onto the virtual machine, so we essentially came up with 3 VMs, 3 virtual machines. 2 virtual machines on the software memory tiering server, 1 VM on the DRAM only server. All 3 virtual machines were set exactly the same. So every VM had 12 vCPUs, 256 gig of of VRAM or VM memory, right? There's only one change we did here. If you look at something in the bottom, and I'm sure it might be visible to the guys in the back, it says NUMA node affinity. Essentially what we did was we pinned the virtual machine to a particular NUMA node. And the reason is we wanted to run this in a controlled environment. We didn't want any kind of noise. So we said, okay, 2 virtual machines on the software memory tiering server, pin it to NUMA node 0, right? And if I move on to the next slide here, we had 1 such virtual machine for the DRAM only server. We did exactly the same. Again, 12 vCPUs, 256 gig of RAM for the virtual machine. Same exact hardware version level, same VM2 level, no difference there. We did the same thing as well. We pinned that virtual machine to a NUMA node 0 of that DRAM server. So you have two VMs on the left-hand side, software memory tiering server, one VM on the right-hand side, DRAM only server, set up exactly the same. All three VMs are pinned to NUMA node 0 to eliminate any kind of NUMA imbalance, any kind of noise, completely controlled environment. Let's run the workload and let's see what the metrics kind of looks like. But even before we go there, one more level, because we spoke about the ESXi, we spoke about the virtual machine. Now we need to talk about the database, right? So from a database perspective, that's what the database looks like. And again, ignore the word where it says SGA. Think of SGA or the Oracle SGA as the Oracle memory. So SGA stands for the System Global Area. Essentially, it's that chunk of memory that Oracle database or any database in this world would basically read blocks from disk onto the buffers, do some kind of operation, and then flush it back, or flush those dirty writes back. That's essentially what it is. So the Oracle memory was set to 192 gig for all three virtual machines. All three VMs had the Oracle Enterprise Linux 8.5 UEK, Oracle latest and greatest version 21.5. I think 21.6 was released recently, so it is almost the latest and greatest version. It was a standalone database. We pretty much made sure that every best practices that we have in recommendation for running Oracle workloads on VMware, that was followed. So made sure that ESXi versions are same, VM versions are same, the Oracle databases are set exactly identical, right? All of the best practices are followed, and we ran the same load generator across three virtual machines, and we'll see that in the next slide here. So, even before I go into the metrics, the load generator that was chosen was SLOB, and for people who are unaware of what SLOB stands for, it's silly little Oracle benchmark. Essentially what it does, it just does physical IOs or logical IOs, right? The name of the game here is to hit the database so hard for physical and logical IOs. You want to push the hypervisor. You want to push the platform to see how much can I get from that platform, right? From that hypervisor. So essentially, if you look here, we set the update PCT, which is to 0. What that means is it's a read-only test, right? There is no writes. It's a complete read-only test because we wanted to compare the performance between the software memory tiering server and the DRAM-only server. And then we set the runtime to like 20 minutes. We ran the workload across all three virtual machines, right? We collected a lot of statistics. So we don't have time to show you all the stats, but we collected stats from the ESXi level, the hypervisor using ESX top. We collected virtual machine statistics. We collected operating system statistics. We collected database statistics, right? And from a database perspective, we are now able to show for one metric. And that metric here in question is that execute SQL per second. And there's a reason why I chose that metric. See, what happens is anytime you want to measure if the performance of a database has increased or decreased when you do a replatforming, right? Or when you move from, let's say, one architecture to the other architecture, maybe from HPUX, Solaris, AIX to over x86. Typically what happens, the Oracle DBAs, especially in the Oracle land, they look at this metric. And they say, hey, when we ran it on this particular platform, it was X. And when we ran it on this platform, it was Y. And X is less than Y, which means my performance has improved, right? Or X is greater than Y, which means my performance has deteriorated. There's something wrong here. I need to go and fix. So this is a very important metric, especially for the DBAs, when they have to measure the throughput of the workload or the performance of the workload. And if you look at the run, so we had two runs. We had multiple runs, but we just picked two runs for illustration here. When we look at run 1 and run 2, right, the VM1, VM2, and it was actually incorrectly said VM1, it's VM1 and VM2 for the software memory tiering. That came very closely for the DRAM. So if you look at the aggregate for software memory tiering, both the virtual machines, the aggregate is more than what the DRAM is able to push. So it's like 60K per second versus 40K per second. Case in point being, I'm able to consolidate. I'm able to pile more virtual machines on that software memory tiering server and run more workload than I could on a DRAM-only server. Because keep in mind, right, my DRAM-only server, NUMA node, had 384 gigs. My virtual machine was 256 gig, which means if I don't want to have any kind of overcommitment from a memory perspective, my virtual machine memory has to be less than equal to that NUMA node memory, which is 384 gigs. But in this case, with software memory tiering, right, we were able to do more. We were able to pile on, right, virtual machine, and essentially run that workload and run more workload, right? And we'll have a look at another metric as well here. So logical read blocks per second. Essentially what happens is every time you do any kind of writes, it's always the physical write, right? When you start looking at any kind of reads, it's always the logical reads blocks per second. And if you look at the test result here, again, the aggregate for the software memory tiering, that was close to like what, 8 million as compared to 5 million across both the runs. So case in point being, you look at execute SQL per second, you look at the logical blocks read per second, the aggregate for the software memory tiering virtual machines is more than what you can run on a DRAM only mode server. So that's from an Oracle database perspective, right? If I have to look from a guest operating system perspective, right, across all three virtual machines, how did the guest OS fare in those, right? You could see here that the last column is the idle percentage, and that basically says how much CPU cycles are idle on the guest operating system. In the case of the software memory tiering virtual machines, you had a lot more idle cycles than what you had in the DRAM virtual machine, which means I did a lot of work with spending few energy with the software memory tiering virtual machines. In case of the DRAM VMs, I had to do a lot of work and I had to spend a lot of CPU cycles, and the idle percentage essentially came down. So that's better CPU utilization from a guest operating system perspective. So workload went up, my CPU utilization is better, my stats are improved. And if I have to bring everything together here, right, if you focus your attention on the software memory tiering VM aggregate, the fifth column, you would see essentially 69K versus 41 for execute SQL. And if you look at the logical reads, that's close to like 8 million versus 5 million. My CPU utilization is much better, right? I get a lot of idle cycles for my virtual machine, which means I could do something else, right? I'm running this workload, I could run another workload on the same VM across the same database, right? So we were able to run 2 such virtual machines on that software memory tiering, especially on that one NUMA node. I'm not talking about the other 3 NUMA nodes. On that one NUMA node on the server, as compared to running one VM on the DRAM only server, right? Yes, we did have the current virtual machine size and capacity constraints solely and wholly because of the fact that ESXi as an hypervisor was able to throw a blanket across those disparate memory components and essentially just present an abstraction layer and said, your total memory is 4.5 terabytes, go forth and conquer. You don't have to worry about your NUMA nodes, you don't have to worry about your hot blocks, your cold blocks, and where you're placing it. In the case of DRAM only server, where you don't have this flexibility of this tiering technology, you as a virtual machine admin or you as an application owner, you would have to size those VM and say, my VM needs to fit here, my VM needs to fit here, because it should not cross NUMA boundaries because there is a memory latency across the QPI interconnect. So again, OS metrics fares well, database metrics, it fares well, everything put together, we see there is a great improvement here as well. So I'm going to move on to the next slide, or probably some of the key takeaways, and Arvind and I have spoken about it as well. So VMware performance results, it shows software tiering is ready for the next phase of the big memory evolution. When we speak about mission critical application, it really doesn't mean the Oracles. It could be the SQLs, the SAPs, or whatever you have running in the shop. That could even be your Java production application as well, right? They benefit from such memory innovations here, right? And software memory tiering, that'll bring scale without adding any operational complexity, right? Of course, CXL, everybody is waiting for the CXL technology that can bring pooling and disaggregation here. I quickly wanted to flash, not this one, sorry. This slide here. So essentially, for people who are more interested in workloads, especially the Oracle Arena on the VMware hypervisor, right? Any and all collaterals on Oracle and VMware, whether it's Oracle with memory tiering, with PV, RDMA, storage and so on and so forth, can be found in this one particular link here. And I'm sure the slides will be available to you after the conference, but I think we are at this point of time where we are ready to take some questions. And please take a moment to rate this session as well. Your feedback is really important to us. But I think we have some time for questions and answers if you guys. So the question is, when is this available for external testing?
Yeah, like I said, we are actually currently in the process of working with a lot of the memory vendors. So we did actually work on an initiative with Intel Optane, but unfortunately we decided not to productize it because of Intel's change in direction. But what we are doing is we have that the essential pieces available. So which means is, that we just have to find the right partner that we can work with and implement this technology. At the same time, we feel that the CXL ecosystem itself is sort of still evolving, and a lot of the OEMs have not really adopted it in their server architecture. So what we are trying to do is work with both the memory vendors and the server OEMs and see where when we can actually sort of get into that market fit, and then at that point we'll be able to release this technology to our customers. Yeah, great question. So the funny thing is we are actually working with NVMe vendors also. So it's not just the memory vendors. So the thing with CXL is that, and the thing with memory is that we could actually take some of the NVMe kind of storage, because if you looked at some of my slide, you would have seen NVMe and NVMe or Fabric. So the way we will work with on those technologies is to find something where we can do a hardware based caching, which means that we'll have DRAM in the middle. We'll also have some hardware logic, maybe in the form of an FPGA or a custom ASIC, that we can actually put, and then we can use in the background. We can actually end up using the NVMe or the storage technology. So that's one of the ways in which we could actually tier to a slower memory. So directly answer your question, what is sort of the range? So we could today we go anywhere from 1:2 to 1:4. Even 1:1 is a suitable one. 1:4 is also suitable. But it really, in terms of the latency characteristic, it just depends on how much we can sustain. We have been able to sustain, sort of the Optane kind of latency or the Internuma kind of latency, a few hundreds of nanoseconds. We have even seen that our operating system itself is really resilient to up to 10 to 15 microseconds. So we can actually sustain, when we get the right kind of hardware caching pieces and the hardware tiering pieces, we can actually sustain much bigger latency, like in the tens of milliseconds also for memory. Actually,
Quickly take a question from the gentleman there.
Yeah, sure. Go ahead.
So this essentially, as I mentioned, if you saw a parameter called update PCT, right? We had set that to 0 because we wanted to compare the performance of DRAM, right, versus software memory tiering, mostly from a read-only perspective. So we could have done the write-only test, but we didn't do that. We just wanted to primarily show that when we do a lot of reads, right, we are able to probably like 1.5 times the amount of the reads or even the logical blocks, right? But I think the time is up, and I can talk to you more in detail kind of outside here, right? But